Welcome back to our flipped chemistry classroom, and we're continuing our discussion of the models of the atom. So we've moved from Dalton's model of the indivisible atom that makes up everything to the plum pudding model that discovered the existence of the electron but thought they were embedded in a positive atom, to the Rutherford model that contained a nucleus that was small, dense, and positively charged and still had those negative particles, electrons embedded in it, to the Bohr model where the thought was that the electrons orbited the nucleus like planets orbiting the sun. And now we're moving into the quantum mechanical model, or the quantum model of the atom. So let's talk about our evidence. So just a quick review. So why do we think that this is the case? And the answer is that we look at atomic spectra. So we look at the light that is given off when you excite an atom, or the light that is absorbed when you shine the full spectrum of light onto an atom. And we get this characteristic spectrum, and the spectrum is different for each element. And so Bohr said the classical view of the atom was wrong, and we need this new theory, and we call this new theory quantum mechanics or wave mechanics. And the basic principle behind quantum mechanical models is that the electron can only exist in certain discrete orbitals. Now notice that we've changed our term from orbits, like Bohr said, to orbitals. And what that means is that the electron is restricted to particular energy states, quantized energy states. So the electron is essentially a bundle of energy. It is both a wave and a particle. So Bohr thought that the electrons orbited the nucleus like planets orbit the sun, but it turns out he's not quite right. They're not orbiting, they're not in fixed positions. They're more like bees around a hive. They're constantly circling it, they're constantly focused on it, near it, getting closer, getting farther, but they're not following a particular path. And so we have to go back to the idea of the electron behaving as a wave. So we go back to Louis de Broglie, who says the electron propagates through space as an energy wave. And in order for us to understand the atom, we have to understand the behavior of those electromagnetic waves. And so we've spent some time talking about the electromagnetic waves and the energy levels of those electromagnetic waves, and how different photons of light carry different levels of energy. And so we have to combine the ideas of de Broglie with Werner Heisenberg, who says, okay, if it's this small of a particle, even just looking at it changes it. Because in order for us to see something, light has to hit it and bounce back to us. And so even that little bit of light is actually going to change the electron. So he says, this is just a summary of his uncertainty principle, that we cannot simultaneously determine both the position and the momentum of an electron. So in other words, we can find out where the electron is, but not where it's going. Or we can find out where it's going, but not where it is. We have a limitation because simply the act of measuring the electron changes the electron. And so we restate the Heisenberg. So he then solves this problem by accepting the limitation that we don't know the exact position, but we can define its energy very exactly. So Heisenberg's uncertainty principle says we cannot simultaneously define position and momentum, but we can define the energy very exactly. And so Schrodinger takes on this challenge. This is Ernst Schrodinger, and he applies the idea that electrons behave as a wave to the problem of the electron in the atom. And he develops the wave equation. And the solution to the wave equation gives a set of expressions that are called wave functions, abbreviated with the Greek letter psi. And each one of these wave functions describes an allowed energy state of an electron. Now, fortunately for you, these are beyond the scope of this class, but I'm going to go ahead and show you one so that you can be grateful that we don't have to do this math in this class. But this is the Schrodinger wave equation published in 1926. There is a finite number of solutions to this equation, and those finite solutions are the quantized energy levels. And this wave function defines the probability of finding an electron. So what's the point of all of this? All of these wave equations, all of this information about not being able to define both location and momentum, not being able to understand the electron without understanding the wave, leads us to this wave equation. And this wave equation defines the electron cloud. It defines the region in space where there's a 90% probability of finding the electron with that given energy. So this is our practical application. The shape, so these wave functions give us three-dimensional shapes that are probably where the electron is located. They are certainly within the energy of the electron. So those energy can be defined in basic energy levels. And we talk about these sometimes as shells, always as energy levels. So it is the probable distance of the electron from the nucleus. It's also known as the principal quantum number. And each shell or each energy level can hold a different number of electrons. And so the number of electrons that can fit in each shell is 2 times the principal energy level squared. So in our first energy level, and you guys all know this already, N is 1, 1 squared is still 1, it can hold 2. And that's why hydrogen and helium only have 2 valence electrons. And you all already know that the first energy level only holds 2 electrons. The next energy level 2, well, 2 squared is 4 times 2 is 8. The next energy level holds 8 electrons. And this all has to do with these shapes that are defined by that wave function. And those shapes are what we call orbitals. So the first orbital is the s orbital. And the s orbital is pretty easy to remember because it has a spherical shape, S for sphere, and it's centered around the origin of the 3 axes in space. So the first 2 electrons in any atom go into this s orbital, this 1s orbital. First energy level, s orbital, only holds 2 electrons shaped like a sphere. Once we move up and we start adding more electrons and we move into the second energy level, the first energy level has 1 s orbital, and the second energy level also has an s orbital, but its s orbital is bigger. And then at the second energy level, we also add a p orbital. And the p orbital frequently is described as being dumbbell shaped. I think of it as more peanut shaped. And there are 3 p orbitals in each energy level above energy level 1. And each one is on one of the 3 axes in space. So it's either the X, the Y, or the one that's coming out towards you, and that's the Z axis. So there's 3 p orbitals. Once we move to energy level 3, we add in d orbitals, and now there are 5 orbitals. They get a little bit more complicated. These are frequently called double dumbbells. I think of them as shaped more like eggs. And so I think of D and dozen. And then our final energy or orbital shape is the F orbital. There are 7 F orbitals, and the F orbitals kind of look like flowers, especially once you nest them on top of each other. So our quantum mechanical model has our electrons arranged in levels, and then into sublevels, and then into suborbitals. As always, if you have any questions, let me know, and I look forward to seeing you in class soon.